Okay, so good afternoon. My name is Latif Khan. So Dallas time is now 1 p.m. Central Standard Time in the United States, and I'm the session chair for this session. This session is Machine Learning and Database 2, session number R27, and in this session we have 5 papers. 1, 2, 3, 4, 5. Yeah, 5 papers. The first paper, so I assume you can hear. So the first paper is 766 paper ID, and the title of the paper is Machine Learning Based Cross-Platform Query Optimization. And the authors are from TU Berlin and QCRI, Qatar Research. So I think Dr. Zoe Kaudi, she's going to present the paper. I mean, it will be recorded lecture presentation first, then she is available to answer your question. So please send your question, or you can ask directly after the presentation. Lynn, you want to start the presentation?
Hello everyone, I'm Zoe Kaudi and I will present you the ML-based optimizer of Rheem, a cross-platform data processing system. So cross-platform systems have become very popular recently, and their main characteristic is that they decouple applications from the underlying processing platforms. There are many systems one can find, and most of them rely on the user to select the platform that he wants his query to run on. There are few systems that go one step beyond and have a cost-based optimizer. The optimizer here is responsible for selecting which subquery will be executed in which part of which subquery will be executed on which platform, with the goal of optimizing typically runtime or monetary cost. So now, what is the problems with cost-based optimization? First of all, the underlying platforms have low control, so we cannot access their cost functions or statistics. This leads to having to define many cost formulas. So for instance, you need to have one cost formula per platform per operator. And usually these cost formulas assume linear functions, which is not always the case with real behavior. In addition, these formulas are composed of many coefficients that the developer has to fine-tune. For example, in Rheem, for just one cost formula and one metric of one operator, a developer has to fine-tune 6 coefficients. So for a platform of, for a number of 3 or 4 platforms, these coefficients can go to hundreds. And this is very hard for the developer to fine-tune. Now, to show you the impact of the cost model fine-tuning, we have conducted an experiment where we fine-tuned the cost model manually, and we have also a simple operator profiling. Here are the difference in runtime. Also, please note that in order to avoid having the cardinality affecting the results, we injected the real cardinalities in both cases. So as you can see, the performance difference can go up to 1 order of magnitude, which is really important in such a cross-platform setting. So how can we ease the users of this tuning effort? Now, with the hype of machine learning, one could say, why you don't replace your cost model with a machine learning model? For instance, in Rheem's cost-based optimizer that takes as input a Rheem plan and outputs an execution plan, that would simply mean to replace the cost model that gives the operator costs with a machine learning model that predicts the runtime of each operator. However, this comes with various challenges. First of all, there is an overhead of transforming each subplan to a vector, and this overhead can become very large, as the enumeration will have to enumerate thousands or millions of plans. And also, all machine learning models required training data, which is also very hard to acquire. So in Robopt, we overcome these challenges first by proposing a vector-based plan enumeration that also comes with a lossless pruning. And we provide also a scalable training data generator to facilitate users in finding training data. Now, the benefits of having a plan enumeration that is purely based on vectors is twofold. First, it avoids this transformation from a subplan to a vector. And second, it can exploit modern CPUs through vectorization. And here we can see some results. We can see the improvement factor of using this vector-based plan enumeration over using the original plan enumeration, but by having replaced the cost model with a machine learning model. Let's now see the general idea of Robopt and how it works. So it takes as input a Rheem plan, and then it uses some feature selection to extract the features in a vector format for this plan. And this plan is given to the plan enumeration, which, as I said before, is done entirely based on vectors. And this plan enumeration is closely coupled with the machine learning model that predicts the runtimes of these subplans. It then outputs the optimal plan in the form of a vector, and then Robopt transforms back the vector to an execution plan. Now, to ease the design of plan enumeration algorithms, we have defined a fine granular set of operators. Then, in this way, we can also exploit parallelism. I will give you more details now. So, for example, the vectorized operation takes as input a plan and outputs its corresponding vector, while the split operator takes this type of vector that corresponds to an entire plan and splits it into subplans. For example, you can split it into the atomic operators. Then the enumerate will take the vectors of these atomic operators and will output their plan enumeration. Now here, a plan enumeration is the set of execution plans that correspond to this operator. For example, if we have the operator map, then the plan enumeration will consist of the vector that corresponds to the operator Spark map and the vector that corresponds to the operator Java map. Then the iterate takes pairs of plan enumerations and outputs a list of pairs of vectors that correspond to the Cartesian product of the execution plans. Then the merge will take each of these pairs and will merge the vectors into a single vector, so which this corresponds in merging two operators together. And of course, the prune operator will take a set of vectors and will prune based on the predictions that the ML model gives. And this operation will continue until the entire plan is built. After that, the optimal plan is given to the unvectorized primitive that will output the execution plan of Rheem. Now, the benefits of these primitives First, we can plug any pruning method we want. In the paper, we propose a lossless pruning that guarantees to find the optimal plan. And also, we have a pruning-aware enumeration strategy where we try to maximize the pruning effect in order to speed up the enumeration algorithm. Now let's see how the training data generator works. First of all, what is training data in our case? So training data here are the plans with their runtimes. Now, getting the runtimes of all plans means that we need to run the plans, and this is really impractical because in an environment with gigabytes of data and big data platforms, this can take weeks or even months. So how can we get the runtimes in a reasonable amount of time? So here is the training data generator architecture. First of all, the user specifies the shapes of the plans that he would like to have in his training data, and the minimum and maximum number of operators. The Rheem plan builder will output Rheem plans and will give them to the Rheem job builder that will output execution plans. And then the most important part comes from the log generator that will actually output the training data, that is the plans together with their runtimes. And to illustrate how it does so, it has two components: the job executor, which actually executes the jobs, and the log completer that actually imputes the values of the jobs that we did not run using interpolation. And for illustrating how interpolation works, for each job we actually run the jobs for a small input cardinality and very few jobs with a large input cardinality, and then we interpolate the values in between. And like this, we obtain the entire set of training data. Now let's see some experimental results. First of all, how Robopt scales as the number of operators increases. And here we can see that first of all, an exhaustive enumeration cannot scale more than 10 operators. While what is interesting here to see is that Rheem with an ML model instead of a cost model, but with the original plan enumeration algorithm, is much slower than even the cost-based approach. So we can conclude from this experiment that vector-based enumeration makes Robopt more efficient and scalable. Here we want to test the effectiveness of Robopt, so how good it is in finding good plans, and we compare it with the cost-based optimizer. The blue, pink, and yellow bars are the execution times of word count in different platforms, while the arrows show which platforms the optimizer chose. And we can see that the ML optimizers, in this case, always chooses the same plan, the same platform, and in some cases, as we show in the paper, it even can choose a slightly better execution plan, but all this without requiring any tuning effort. And finally, here we can see an experiment where we allow Rheem to choose two or more, a combination of platforms for one query. Here we have k-means. And we can see that Robopt chooses a plan that is superior to the plan chosen by the cost-based optimizer by combining Spark and Java. So to summarize, the Robopt Rheem's ML-based optimizer is heavily based on vector-based plan enumeration. And we have defined a set of fine granular enumeration and pruning operations. We also provide a scalable training data generator that uses interpolation to avoid executing all the jobs. And with this, we obtain an optimizer that is both efficient and scalable and does not require any manual tuning. Thank you very much.
Okay, thank you. So do you have any question? I'm not sure whether there's any question, but let me ask you a question. When you use as let's say if in a distributed environment, some of the machines become Straggler, so becomes very slow all on a sudden, then what will happen in your scenario?
Rheem, in that case, relies on the underlying platform to deal with these straggler nodes. So it's like, you can see it as a middle layer between the application and the underlying platform. So the underlying platform is responsible for any kind of optimization, let's say, regarding straggler nodes or fault tolerance or things like that.
Yeah, it's very good, useful work. Thank you. And did you take into consideration any caching stuff in your query optimization?
Excuse me, can you repeat?
Yeah, caching, like instead of putting the data in the disk, if you put the data in the main memory. But that may not be relevant here anyway. Thank you. That's fine.
Okay, thank you.
So now we are moving towards the second paper. The paper ID is 858, Automatic View Generation with the Deep Learning and Reinforcement Learning. And the authors are from Tsinghua University in China.
Hello everyone, my name is Haitao Yuan. Coming from Tsinghua University, I'm glad to share our work with you. The title is Automatic View Generation with Deep Learning and Reinforcement Learning. Next, I will give my presentation according to the outline. There are 6 parts. The first is the motivation, and then we will introduce some preliminaries. Next, we give the system framework. In the system, we mainly design the cost estimation model and the view selection model. Finally, we give a brief summary. So let's first see the motivation. The first question is what and why automatic view generation. As we all know, the analytical circle queries share common subqueries, and building views on these subqueries can avoid redundant computation and improve the performance. Please look at the example. The figures are plotted based on a real-world workload in Alibaba Cloud. From the 2 figures, we can conclude that there actually exist many redundant computation in real-world workload. So our goal is to automatically select highly beneficial subqueries to generate materialized views. The reason is that manually generating materialized views are not scalable to a large number of database instances, especially on the cloud database. Thus, we need to think about 3 new questions. The first is what does highly beneficial mean? And the second is how to measure the benefit. And the last is how to let machines make decisions for selecting highly beneficial subqueries. We will give our answers on in this paper. Okay, let me show you some preliminaries. First, some concepts should be claimed. A query means a circle statement, and it can be parsed into an abstract syntax tree. We regard each subtree as a subquery. In addition, the tree can be transformed into a plan, while each subquery can be transformed into a subplan. Thus, we use plan or subplan to represent a query or subquery in this paper. For a query or a subquery, we first consider the fees of CPU usage and the memory usage. We measure them with money, so we can regard the cost as the summation of these fees. Last, I'll explain the important concept materialized view. As we all know, materialized view means storing the corresponding query results of the view. So the overhead of materializing a view contains two parts, the storage cost and the query cost. Given a view, the storage cost means the space overhead because we need to spend money to store results, and the query cost is represented with the cost of its corresponding subquery. In summary, we define the total overhead as the summation of the two costs. As for the benefit of using a materialized view for a query, we define it as the query cost gap before and after using the materialized view for the query. As for using multiple views for a query, we can compute the total benefit with the summation of each view's benefit for the query. However, we cannot ignore a constraint, which is that if two subqueries have overlaps, we call them overlapping subqueries, and they cannot be used to answer a query together. So any two views used together for a common query shouldn't be overlapping. Therefore, given a set of materialized view and a query workload, we can compute the utility of using these views for the workload. In details, the utility is computed by the total benefit minus the total overhead. Each materialized view is built on an associated subquery, and thus we can estimate its overhead with some existing method. However, the challenge is that it's not realistic to obtain the benefit due to the cost after using the view cannot be estimated directly, which is also the first challenge. And let's review the selection problem. The problem contains two optimization objects. The first is to select optimal subqueries to generate views, and the second is to select optimal materialized views for each query under the constraint. Look at the formulated definition. We select the subject S from candidate set SQ for the first object, and select the subset VQS from VS for each query. Therefore, the challenge is how to solve this problem effectively. Okay, I'll explain our solutions. Before that, I first choose the whole framework of our proposed system. Look at the figure. The system mainly contains three parts, which are the pre-process part and the online recommendation part and the offline training part. In the pre-process part, we first pass query statements into planes and then extract subplane as subqueries. Later, we use equivalent detection tools to infer whether two subqueries are equivalent and then collect equivalent subquery pairs. Next, we group equivalent subqueries into a cluster. For each cluster, we select the subquery with the least overhead as the view candidate. In other words, for each cluster, we only need to build a materialized view on the candidate and then can reuse the materialized results for other subqueries. In the online recommendation part, we first design a deep learning model to estimate the cost or utility, and then leverage a reinforcement learning model to solve the view selection problem. In the offline training part, we offline train the above two models. After generating materialized views, the system would rewrite queries with views and then executed the rewritten workload to get results for clients. Also, this process would generate some metadata, which are stored in the metadatabase for offline training and online recommendation. Therefore, the solution to the two challenges are respectively using deep learning and using reinforcement learning. Therefore, I'll present the two models in details. The first is the cost estimation model. Given a query and a view, the goal of this model is to estimate the cost of the new query after rewriting the raw query with a view. And first, we should understand the features we can use. There are two kinds, the planes and the associated tables. Planes contains a query plane and a subquery or view plane. Each plane can be regarded as a two-layer sequence. So we sequence and the associated tables mainly include two kinds. The first is called the schema of tables, such as table names, column names, and types. The second is called the statistic of tables, such as the number of tables and columns and the size of records. And after that, look at the picture. We implement a wide deep model, which is composed of a wide linear model and a deep nonlinear model. The wide linear model aims to capture linear relationship between the estimated result and numerical features, and the deep model aims to capture the nonlinear relationship. In particular, only numerical features have linear relationship, so we first normalize them to eliminate the difference in the magnitude of feature values. As for nonlinear features, we design different models to encode them. For example, the table schema only contains keywords, so we first use the keyword embedding to encode each keyword and then apply the average pruning to get a fixed length representation. However, plans include not only keywords but also strings, so we also need to design a string encoding model. Especially giving a string, we first embed each char, then apply the convolution neural network and average pruning to get a fixed length representation. After embedding keywords and strings, we regard the plan as a two-layer sequence, and then use the sequence model to further encode them. Next, we concatenate all features representations and apply the ResNet blocks to convert them into the final representation. And last, we use the regressor to estimate the cost based on the final representation. And last, we have done some experiments to evaluate the effectiveness. We use 3 workloads and 4 baselines. The first 2 baselines compute the cost by this formula. The difference is that one uses query optimization and the other uses the state-of-the-art deep learning model. The last 2 baselines use traditional machine learning methods to estimate. Also, it compares the different paths of our models. Different paths effectiveness of our models. We make 3 variations of our model. The first has no keyword embedding, the second has no string encoding model, and the last have no sequence encoding model. Finally, we compare these methods' performance. The results show that our methods outperform others. Next, I will present the view selection model. First of all, the materialized view selection problem is converted into an integer linear program problem. In the ILP problem, we aim to optimize the 0, 1 variables z and y intuitively. We can use existing ILP solver to get the exact solution, but the issue is that it's intractable for very large workloads due to the number of integer variables. Therefore, we propose an approximate method which optimizes the variables z and y iteratively. And first, we randomly initialize z and y. Next, we iteratively update the value of z and y with the function zopt and yopt. In the OPT function, for each subquery Sj, we compute the probability to flip its variable Zj based on current states. In the YOPT function, for each query Qi, we build a local ILP problem and then use the ILP solver to get actual solution for the local problem, which means updating the variable Yj. However, that still contains an issue, and the issue is that this function has no memory ability and cannot convert to a global optimal solution. To address this issue, we regard the iterative optimization process as a Markov decision process. And shown in the figure, the state is defined as the tuple of z and y. The policy is defined as selecting tuple of z and y. The policy is defined as selecting a subquery, and the action is to flip the value of the corresponding variable zj. The immediate reward is defined as the gap of utility before and after taking the action. Therefore, we can apply some reinforcement learning method to solve the problem. Actually, we use the deep Q network method. And first, we get the initial state E0 with the function iter view and randomly initialize the parameters of the DQ model. Later, we execute the in reinforcement learning process with N2 epochs. In each epoch, we iteratively get optimal states based on the initial state E0. In each iterative step, we use the decoy model to update Z and then use the function YOPT to update the Y respectively. Each epoch terminates when the immediate reward is not increased. We can of 9 train the DQN model with the function DQN. Okay, we compare our method with 5 base 9s. The first is the state-of-the-art method, which builds a bipartite graph for queries and subqueries, and then iteratively labeling vertices and edges of the bipartite graph. And the rest of the method belong to greedy method, which sort candidate subqueries based on different strategy, and then select top K subqueries to materialize. In particular, we use 4 different greedy strategies, which are called top K frequency, top K overhead, top K benefit, and top K normalize. We also use the 3 workloads to evaluate their effectiveness. And first, we do experiments to find the optimal K for each greedy method. We can find that all curves first raise up to the maximum point and then fall down. Later, we also compare the convergence between our proposed 2 methods. The results demonstrate that the IO view can keep the utility stable on the 2 workloads. Next, we compare the saved cost for the 3 workloads with different methods. There are 2 measurements, utility and ratio. The results shows that our method has optimal results. And last, we implement the end-to-end system, which considering both the cost estimation model and the view stage model. To evaluating the effectiveness, we compare 4 combinations. Among them, the last combination is the imputation of our system, while the first is the current state of the system. The results show that our methods outperform the state of the art on the 3 database sets. Finally, let me give a brief summary of our work. As listed on the slides, we first formulated the problem and regard it as an ILP problem with constraints. Then we proposed the cost estimation model and the view stage model to solve the 2 challenges. In the first model, we consider query view plans and associated views, and then proposed effective encoding models and implement the wide deep framework to solve it. In the view stage model, we implement the iterative optimization method and then convert the optimization process to MDP. And last, we apply the decoy method to solve it. That's all. Thank you for your listening.
I don't see any question in the Slack. So do you have any question? Please feel free to ask the speaker. Any speaker is here online?
Yes. Can you hear me?
Yeah, we can hear you. Yes. Any question from the audience? Okay. Since no question, let me ask a very basic question. So I saw you use deep learning and also reinforcement learning. And in your slide, you showed why do you need deep learning? Why do you need reinforcement learning? Can you tell me one more time?
The deep learning is to solve the problem. The problem is that we need to estimate the benefit. We using a materialized view for query. So it's better to use deep learning to solve it. And the reinforcement learning and the reason of using the reinforcement learning is that the problem of the view selection can be formalized as an ILP problem, and now the current ILP solver cannot solve it when the data is large. So we use an approximate solution to solve it, but the solution cannot converge into a stable solution. So we can formalize so we can convert it into a Markov decision process, which can be solved by the reinforcement learning. So we use this technique.
Okay.
Okay, thank you.
Thank you. So now we are at the third paper in this session. So paper ID 33, ColumnSGD, a column-oriented framework for distributed stochastic gradient descent. And this paper, we have speakers, the authors are from Peking University, Microsoft Research, Tencent company, and then ETH Zurich, I think. So I don't know who is going to so we'll play the recorded lecture first, and then at the end you can ask questions. So Yugang and please play the video.
So good afternoon, everyone. I'm Zhipeng Zhang from Peking University. Today, I'm going to talk about our recent work on ColumnSGD, a column-oriented framework for distributed stochastic gradient descent. This work was done with Bin Cui from Peking University, Wentao Wu from Microsoft, Le Yu from Tencent, Jiawei Jiang and Ce Zhang from ETH. So in this work, we focus on training large models in distributed machine learning. As we know, when training large models, existing machine learning systems like PaToM and MixNet usually partition the training data by rows and store the model in the master node like figure A. In which case, the workers and the master needs to exchange gradients and models, which could lead to huge communication cost. To handle this, we propose ColumnSGD, a column-oriented framework for distributed SGD. In ColumnSGD, we partition the training data as well as the model by columns to all workers. Moreover, the master does not hold the model. Rather, it is only responsible for scheduling and aggregating statistics from workers. ColumnSGD has two benefits when it comes to large models. First, the communication cost of ColumnSGD is small. It is only related to the batch size. Meanwhile, the model is offloaded to all workers, thus the master is lightweight. ColumnSGD supports models including logistic regression, support vector machine, factorization machine, multi-layer perception, and so on. Our experiments show that ColumnSGD is faster than SparkMLib by 930 times, PaToM by 63 times, MixNet by 14 times. Here is the outline of this talk. We first present the background of SGD. SGD is a widely used optimization method and has been implemented in most of the machine learning systems. The pseudocode is as follows. SGD is an iterative process. In each iteration, we first sample a batch of training data. Then we use the data to compute the gradient. Finally, we use the gradient to update the model. When it comes to distributed SGD, it is actually asking that how to parallelize the computation of line 3. In the distributed execution, we need to consider a few questions, like how to partition the training data, how to partition the machine learning model, and how to synchronize it. To answer the above questions, existing machine learning systems adopt a RowSGD solution. As shown in the figure, RowSGD partitions the training data by rows to multiple workers and let the master own the model. When training machine learning models, the master first broadcasts the model to workers. Then each worker uses the model and its local data to compute the gradients. Finally, the master aggregates the gradients and updates the model. There could be two challenges when using RowSGD to train large machine learning models. The first one is huge communication cost between the master and the workers. The second one is that the master needs to hold all the model, thus the memory overhead on the master is huge. To deal with large models, we propose ColumnSGD. Our insight comes from the computation pattern of gradients. We find that there are two different ways to parallelize the gradient computation, and one of which is never explored. We take logistic regression as an example. Given model W and a batch of training data XB, the gradient of the model W over XB is computed as follows. we note that there are two sum operations. The first parallelize the computation among data points, which is exactly the one used in RowSGD systems. However, we could also parallelize on the second sum operation. That is, we parallelize in each data point. This parallelization schema is never explored. Based on this, we propose ColumnSGD. In ColumnSGD, we partition the training data by columns to multiple workers. Meanwhile, to support the computation of gradients, we also partition the model by columns. Based on this partition strategy, we design a column-oriented execution plan for SGD. When doing distributed SGD, we avoid sending gradients or models between workers and the master. Rather, we exchange some statistics, as shown in the right figure. In each iteration of SGD, each worker first computes the partial statistics based on its own data partition and model partition. After that, the master aggregates the statistics and broadcasts them back to workers. Finally, each worker uses the statistics to update the model. Now we show the execution flow of ColumnSGD. As a reference, we also included the execution flow of RowSGD. This figure shows an example of training logistic regression using one master and two workers. The batch size is 4 and eta is the learning rate. As we can see in RowSGD in the left figure, worker 1 owns the two data points x1 and x2. Worker 2 owns x3 and x4. The master owns the model W. When doing SGD, each worker first pulls the model W from the master, then they compute the gradient following this equation. After that, they send the gradients G1 and G2 to the master. Finally, the master updates the model. For ColumnSGD in the right figure, it is a bit more complex. Each worker owns one piece of the 4 data points. For example, worker 1 owns the first half of the features of 4 data points, like x11, x21, x31, x41. Moreover, each worker owns one model partition. For example, worker 1 owns W1, worker 2 owns W2. When doing SGD, each worker first computes the statistics. For example, in logistic regression, it is a dot between the model and the feature vector. Then they push the statistics S1 and S2 to the master. After the master finished aggregating statistics from all workers, each worker pulls the sum of the statistics from the master and updates the model. We now summarize the difference between RowSGD and the ColumnSGD. In summary, they have 3 differences. The first one is the strategy for partitioning the training data. In RowSGD, the data is partitioned by columns, by rows, while in ColumnSGD, it is partitioned by columns. Second, in RowSGD, we use a master node to store the whole model, while in ColumnSGD, the model is partitioned to multiple workers. Last, in RowSGD, we exchange gradients and models between the worker and the master, while in ColumnSGD, we only exchange statistics. So ColumnSGD has 2 benefits. The first one is cheap communication. Its communication cost is only related to batch size, which is a hyperparameter and often set as 100 or 1000. The second one is that there's almost 0 memory overhead on the master. Next, we present the system implementations of ColumnSGD, including an efficient row-to-column data transformation method and an algorithm to harness stragglers. So far, we have assumed that all the data is already partitioned by column on each worker. However, many real-world datasets are stored in a row fashion. Thus, we need an efficient algorithm to transform row-stored data to column-partitioned ones. To handle this, we proposed a block-based column dispatching method. As shown in the right figure, the master first organizes the row-based training data into a queue of blocks according to the metadata of the input file. Then whenever a worker is idle, it reads in a block and split it into k worksets. We further organize the workset into a CSR format to compress it. Finally, the workers incur a shuffle operation to send each workset to the corresponding worker. Next, we show how to handle stragglers in ColumnSGD. Stragglers are common in distributed machine learning. In RowSGD, we have flexible synchronization strategy like staleness synchronous parallel or asynchronous synchronous parallel. So our problem in ColumnSGD is that can we tolerate stragglers and how? Here we use backup computation. That is, we let each worker do some extra computation and such that we can recover the needed results even the input of some stragglers are lost. The idea is borrowed from the gradient coding theory. To tolerate S stragglers, we need S plus 1 backup computations in each worker. Suppose we have k workers and we want to tolerate one straggler. The right figure shows an example of ColumnSGD without and with one backup computation. Here M stands for model partition and D for data partition. Figure A shows that ColumnSGD without backup computation. As we can see, if worker 2 is done or needs extremely long time to finish the job, then all of the workers have to wait before the next iteration. Figure B shows ColumnSGD with one backup computation. That is, we partition the workers into k/2 groups. In each group, there are 2 workers and they serve as backup for each other. For example, when worker 2 is a straggler, the master can just proceed to the next iteration without waiting for worker 2, since worker 2 already contains the information of worker 2. We finally presented the experimental results. The cluster we used has 8 machines, each with two CPUs and 32 gigabytes memory. The bandwidth is 1 gigabits per second. We use 4 public datasets, including Avazu, KDDB, KDD12, Creto. WX dataset is from our industry partner. We evaluate all baseline systems on logistic regression, support vector machine, and factorization machine. The baseline systems include MLlib, MLlib star, Python, MixNet, and a prototype system of ColumnSGD on Spark. So the above 2 figures compares ColumnSGD with RowSGD systems on logistic regression on Avazu and the KDD12 dataset. We can find that ColumnSGD is the fastest among all baseline systems. Moreover, the table below summarizes the time cost per iteration of all baseline systems. We can find that ColumnSGD is faster than MLlib by up to 930 times, Python by 63 times, MixNet by 6 times. We also compared on factorization machines, which has a much larger model than logistic regression. Here, F is a hyperparameter. The larger F is, the larger the model is. We observe that ColumnSGD is faster than MixNet by 14 times on KDD12 dataset, when increasing F to 50. MixNet fails to train the model, while ColumnSGD can still finish one iteration in 0.15 seconds. So the code is open sourced on GitHub. For more details about it, please check out the paper. So thanks.
I don't see any question. It's like, do you have any question? Participants, please feel free to ask question directly. Okay, let me unmute all of you, then you can ask question. I unmute all of the participants. So if you have any question, please feel free to ask the speaker.
Ice cream each. यहाँ पे एक आइसक्रीम मिलती टैलेंट तो यहाँ पे एक आइसक्रीम मिलती है बेन एंड जेरीज करके काफी फेमस है यहाँ पे.
Okay. Since we don't have a question, so I have a very basic question. So if you have a if you have a lot of attributes or features, then you will get more benefit using this column-oriented partitioning and so on. But if you have only few columns or few attributes, then what will happen?
Hello, can you hear me?
Yeah, can you hear me? My question.
Yeah. So if the input vector is very small, RowSGD systems is a better choice, because the more things are the computation is more expensive. So ColumnSGD may fail to beat RowSGD systems. They are in a trade-off space.
Mm-hmm.
Yeah, if the input feature
and there is always overhead at the beginning when you do some partitioning, right? Column oriented.
Yeah, yeah.
But that is only one time cost.
Yes.
Okay. Okay. Thank you very much for your presentation.
Okay.
Okay. Now let me go to I think we have 2 more papers to go. Okay, so the second last paper in this session, the paper ID will be 164 in database connected component analysis. The presenter is Harlal Bogalas. He's here. He's from Monash University in Australia, Melbourne, Australia. So I think their time is like 4 a.m. or 5 a.m. So he's kind enough is going to present the work. Thank you. I think he will play a recorded lecture will be played first, then he is available to answer your question.
Welcome. My name is Harald Bögeholz, and this is joint work with Michael Brand and Radu Alexandru Todor. This talk has 2 goals, and we've put them both in the title. The secondary goal is we want to demonstrate that for running calculations on big data, a relational database is a viable or even better alternative to other platforms such as Spark and MapReduce. And the primary goal is we present a new algorithm for labeling the connected components of a graph. So when I speak of a database, I'm talking about a massively parallel processing relational database such as this here. So it runs on a cluster of machines in a distributed way, and each machine has their own storage and, more importantly, their own computational power. So by using this computational power available in the database, we're able to efficiently execute algorithms on big data. So in industry, much of business data is already present in this kind of database. Companies have their data warehouses with lots of data, and the way to run a computation on a subset of that is usually you export it to some specialized infrastructure such as a Hadoop cluster, and then run your computation using MapReduce or Spark, and then possibly re-import the data back into the relational database for further analysis. Now we propose to run the computation directly in the database, thereby reducing the overhead of exporting and re-importing. We avoid consistency issues because we don't have to duplicate data. But most importantly, we can scale our algorithm out to big data, because the database will grow with the amount of data that needs to be processed. So if you have a large data set, then you will also have a large database cluster. So if we manage to write our algorithms in such a way that they will scale to big databases, they will automatically scale to big data. And of course, databases are a mature technology that's been around for a long time, so it's a very good basis to build on. So connected components of a graph, I think, so when I say graph, I mean a network of nodes and links between them, or I call them vertices and edges. And the connected components, maybe I'll explain them by example. So in this graph you see here, we have 2 connected components. The 7 vertices on the left are all connected to each other by some path, and also the 3 vertices on the right. And there's no path between any of the left and any of the right vertices. So these are 2 components And the problem here is to label them, to label each vertex so that the labels are identical for vertices in the same component and different if they are in different components. The labels don't have to be 1 or 2, they can be arbitrary as long as they're different for different components. So how do we represent such a graph in a database? The natural way to represent it is as an edge list, so a database table with 2 vertices per row describing the edges. And the output of the algorithm will be another database table for each vertex, a component identifier or a representative. So now our algorithm works with the following idea. So we take a graph and we contract this graph to a smaller one, preserving connectivity. And we do that until every component is reduced to an isolated vertex. And if we look at an isolated vertex, we know that it is a connected component by itself. So the key here is that this is a transformation that works on the whole graph in parallel, as opposed to other algorithms where you start at a vertex, do something with it, go to its neighbors and the like. So here we work on parallel on the whole graph, and that's how it scales to distributed to a distributed setting. So the algorithm works like this. For every vertex, looks around its close neighborhood. So, and by close neighborhood, we mean the vertex including the neighbors including the vertex itself. So number 6, for example, we'll look around and we'll look here. That's a close neighborhood. And we'll pick the minimum vertex in its neighborhood. So number 6 will pick number 5 as a representative. Number 1 will look around and pick itself as a representative. Number 10 has number 1, and so on. So every vertex picks a representative from its close neighborhood. And that is a table shown here. And you can almost see the SQL query leading to this table. It's essentially select minimum W group by V with some technical details. But so it's a simple SQL query giving us these representatives. Now we contract the graph. We contract vertex sets as shown here by the orange bubbles. So all the vertices that have the same representative are contracted to 1 vertex each. And we do that by transforming the edge table. An edge between, say, vertex 5 and vertex 7 gets changed to an edge between 1, the representative of 5, and 5, the representative of 7. So again, you can almost see the SQL query here. We just join the edge table with this representative table here twice on both vertices, and then we just replace the vertex ID. So that transforms our graph. We eliminate duplicates, and we get a smaller graph, in this case, with 4 vertices like this. Now, the isolated vertices can be removed because they are known to be a connected component by themselves. And then we repeat this step, and in the next step, every vertex will choose number 1 as a representative, and we're done. So now how do we get the end result from this? If we look at these representative functions as mathematical functions, the result is just the function composition. So each vertex gets sent through the function R1 and then R2, and then that gives us the final result. Or if you look at it from a database perspective, it's a join between these representative tables, in this case 2 of them, this one and this one. And we have to make it an outer join, a left outer join, because we have removed isolated vertices from computation. So number 9, for instance, gets mapped to 2 in the first step, and then it doesn't appear in the next table, so we have to just keep it using an outer join. So 9 is mapped to 2 in the end. So a left outer join gives us the result in this case. The algorithm took just 2 steps to finish. Unfortunately, there is a worst case problem with this algorithm. So if we have a linear, sequentially numbered path graph, then every vertex will choose its left neighbor as a representative. So the first 2 will be contracted, but the rest will still stay separate. So we need, for a graph with n vertices, we need n-1 steps until it's finally fully contracted, which is a big problem for big data. On the other hand, if the graph were numbered differently, the same graph just had different vertex IDs, then it would contract much better. As we can see here, every 3 vertices contract to 1 vertex. And you can imagine a long path being numbered this way will contract to 1/3 of its vertices. And if it's numbered optimally, it'll contract by a factor of 3 at each step, which is much faster. So we'd like to be able to number our graph so that it contracts quickly. How do we do that? Well, we can't know, so we guess. The solution is we randomize the vertex IDs at each step to avoid this worst case behavior. So we present 3 different techniques to do that in practice, and we prove that for any input graph, 1 step of randomized contraction will reduce the number of vertices to at most 3/4 of the current number. So the graph will shrink to at most 3/4. So overall, we get an algorithm that is randomized. It's a Las Vegas algorithm, so it always gives us the correct result. It takes a logarithmic number of SQL queries and expectation. It takes linear space. It is robust. There's no worst case input. That is, so when we say in expectation, we mean in expectation, not in expectation over all inputs. So, but for any input, the expectation is over the random choices the algorithm makes. So there's no worst case that will stop our algorithm. And of course, this can be implemented well in an NTP database. So we've run this algorithm on several data sets, and I will just pick one example of an application of this algorithm, and that is the cryptocurrency Bitcoin. So Bitcoin has been around for more than 10 years, and it's essentially, so the Bitcoin blockchain is essentially a big ledger recording transactions between entities. And at the time of this research, it was 250 gigabytes in size. And the importance of these other numbers is just that they are big. So there's 1 billion things here, 400 million things here. So we are talking about a sufficiently big graph to demonstrate our algorithm. So Bitcoin blockchain consists of transactions, sending money from inputs to outputs. So these circles here represent amounts of money, and the squares represent transactions. So a transaction can take some money from here, from some inputs, and put it into some outputs. So that's essentially how it works. And so Bitcoin is pseudonymous. So with each of these circles is associated a Bitcoin address, which we here display as a 1-digit number, but actually it's a long random public key. And one basic question in Bitcoin research is, how do we find out which addresses belong to the same entity? And there's a powerful heuristic to do that. So if a transaction takes inputs from several addresses, then we can assume that these addresses belong to the same entity. So finding out which addresses belong to the same entity is just done by running connected components on a graph that just considers the inputs of all transactions. And as an example here, we can see address number 8 and address number 7 belong to the same entity because they are connected by a path, and that's found out by our connected components algorithm. So that's a practical application. When we run that on the Bitcoin blockchain, we find that there is a large number of single-use addresses. This is cluster size and number of clusters. And you can see there are a few very large clusters. Those belong to Bitcoin exchanges, and actually they have an interesting distribution. So here we're talking about efficiency. So we compared our algorithm with 3 other state-of-the-art algorithms for calculating connected components in the distributed settings. And here are their theoretical, their proven space and time requirements. So the number of rounds and space. So Hashtamin and Cracker, as we can see, they have V squared space in the worst case. So they are not really suitable for big data, because if you input a worst case, your database will just explode. The two-phase algorithm is better in that respect, but it has log square number of rounds. So our algorithm is in expectation better than any of these in theory. And in practice, if we run it, we can see that running it on the address graph of Bitcoin with 900 million vertices roughly, we can see that these are runtimes in seconds, so our algorithm is significantly faster than the others. We also ran it on the whole Bitcoin graph, and hash2min didn't even finish within 24 hours on that graph. So we ran it on 10 more data sets and also did some scalability experiments. So overall, we are presenting a new algorithm that runs in a generic SQL database, no special graph database required. It outperforms the state-of-the-art algorithms in running in the database. It is robust. There's no worst-case scenario, so it always runs in expectation within the claimed number of rounds and with the claimed space usage. Also, it smoothly scales out to big data. So the runtime is quasi-linear in the number of vertices. So we've done experiments with the same type of graph with increasing size, and we can see roughly a linear correspondence between runtime and number of vertices. And that is because in this algorithm, each step runs on a smaller graph. The size of the graph is a geometrically decreasing sum. So if you add that up, it's overall linear, and if the time for a query is roughly proportional to its size, then it is to be expected that the runtime is linear. That's what we mostly see in experiments. Thank you very much.
Yeah, thank you. So the speaker is already here. He's joining from Melbourne. I'm going to unmute all the participants. So if you have any question, please ask him directly now.
Can
you ask a question? I'm hearing eyes, but
अब मतलब कितनी बार तुम बात करोगे इस बारे में मुझे नहीं करनी बात।
I think they're not at all. Okay, so I don't see any question also at the chat, but anybody has a, okay. So my question is a very basic question. So you showed an application in the Bitcoin domain. So in the graph, if we find all this component in case of Bitcoin, how this will be useful, those small component or subgraph?
So there is a lot of research going on about Bitcoin, and this was not my main objective, but the application here is to find out to de-anonymize Bitcoin. So we want to know what's going on. We want to detect money laundering. We want to know all these different amounts of money that are in the system, if they actually belong to the same person. So like some people try to hide their finances by using different addresses and just transferring them between different addresses. And so that's one technique for money laundering. And one basic heuristic for finding out which addresses belong to the same entity is just running connected components on the Bitcoin transaction graph. That's the first step. So there are more sophisticated methods, but for us, this was good enough as an example of a large data set.
Okay, thank you. Anybody has any other question? Bojo, you have any question? I saw you online. No, okay. That's fine. So thank you very much, Harold. So now we are moving towards at the end of the session. We have one more paper. So the paper ID is 568. Towards factorized SVM or support vector machine with Gaussian kernels over normalized data. And all the authors from Zhejiang University, I think from China. There's another one author from Shanghai Jiaotong University also. Okay, so we will play that video first, and then at the end you can, if you have a question, please ask the authors.
Hello everyone, my name is Ke Yang. I'm from Zhejiang University. The title of my presentation is Towards Factorized SVM with Gaussian Kernels over Normalized Data. The outline of my presentation is listed here. First is the motivation of our problem. Nowadays, there is an emerging trend of integrating machine learning and database system technicals. In machine learning area, almost all the machine learning tools are showing that the input of machine learning algorithms is a single table. However, many real-world datasets are stored as multi-tables due to the normalizations in the database systems. Here we give an example. The analysis of a product company wants to predict MUI valuations. They would like to build the support vector machine SVM using the large rating tables. The schema of rating tables include audience ID, MUI ID, and the ratings. Here, audience ID is the key attributes of an audience, and MUI ID is the key attributes of a MUI. The two attributes are filling keys which refer to the two separate tables storing information about audience and MUIs. The audience tables include audience ID, occupation, and etc. The schema of MUI tables including MUI ID, titles, and etc. The analysts would like to join the three tables because they think the detailed information about audience and MUIs might be helpful in predicting the MUI ratings. Hence, the analysts join the three tables as a single temperature tables and input it into machine learning tools and train the SVM models. This processing is called learning after joins. However, the learning after joins would lead the data redundancy avoided by the database systems, and it indicates the poor integration between machine learning and the database systems. In this paper, we aim at studying Factorized SVM. SVM is a standard classification tool in both machine learning and data mining. It often maps data to a high-dimensional space and then employs Gaussian kernel functions to get a nonlinear classifier. Towards this, two challenges have to be addressed. The first one is how to factorize the Gaussian kernel to base tables. The Gaussian kernel function is difficult to factorize since it is complex. Besides, there are two common optimization methods to run the nonlinear SVM models. The first one is gradient descent, and the second one is sequential minimal optimization. The second challenge is how to factorize the step of GD and SMO over joins. Next, I introduce the related works about this topic. There are three kinds of existing methods for SVM. First is many effects in machine learning area focus on improving the efficiency of SVM with the mathematical tricks. This is not our target. Our target is making use of the structural properties of normalized data to speed up SVM learning. Second, there are many commercial and open source systems in database communities to support large-scale machine learning on the top of RDBMS or distributed platforms, such as Randomized, MLlab, and SystemML. Besides, several effects on accelerating machine learning algorithms over relational data have also been proposed. They mostly focus on the nonlinear. They mostly focus on the linear models and cannot be extended to nonlinear SVM with Gaussian kernels straightforwardly. Our approach is the first attempt to factorize SVM with Gaussian kernels over normalized data. Next, I introduce some preliminaries about SVM and the normalized data. The goal of SVM learning is to find a hyperplane that separates the positive and the negative examples in feature space with the maximum margin and meanwhile with the minimum misclassification errors on training examples. Towards this, we can give the primal form of SVM. Besides, we could use the dual forms of SVM in the below to apply the Gaussian kernel functions in the metric queue. In this paper, we are particularly interested in the Gaussian kernel, since it's the most common used kernel. In the context, we assume the training dataset are stored as normalized data in multi-table databases. We call the main table with the entities to train SVM models as entity table denoted by S. There are k other tables called attribute tables denoted by I. The schema of S including SID label Y and feature S in table S, and k other foreigner keys refer to the I. The schema of I include ID and the features in table I. The joined table of table S and table I is denoted by T. T include label Y and the features from table S and table I. For ease of simplifying the presentation, we introduce two table join in the presentation. We discuss the generalization of our method to multi-table joins in our paper. Please refer to the paper for more details. In the following, we overview the workflow of factorized SVM with Gaussian kernels over normalized data. We call this method FSVM for short. First, we give the key insight. Given two factor vectors x and z in table T and the Gaussian kernel function kxz, we can factorize the Gaussian kernel functions into two parts. Kxz is equal to kxszs times kxrzr, where the vectors are the concatenation of its corresponding factor vectors in table S and table R. This shows that Gaussian kernel functions can be divided into two parts that are independent in table S and table R. Based on the key insight, we could give the workflow of the proposed FSVM in the figure. In step 1, given a feature vector Z in table T, we compute the partial Gaussian function values K for each record in the table R and stored those values in the new table PR under the partial coherence with the key RID. In step 2, we join the table PR and S with RID as the foreigner key and compute the entire Gaussian kernel functions. On the fly, we generate a new table TK to store the Gaussian kernel function values under the kernel coherence with RID with the key SID. This workflow could be used in two optimization methods for SVM learning. Next, we present the detail of FSVM and show how to factorize the optimization method. Due to the time limitation, we introduce the GD method as an example, and the SMO method could be factorized in the similar way. Picasso is one of the most efficient methods to solve SVM on GD. We give Picasso as an example for our method. It takes a training example dataset and a number K of international runs, and it outputs the optimized arguments alpha. The kernel function computation could be divided into table S and table R independently as the workflow I just mentioned. By this, we could reduce the CPU cost for Gaussian kernel functions and avoid the data redundancy. In the computation processing, it's inefficient to access the table for data in every steps. We use a multi-metric logic data type, so-called normalized metric, to present the data in the tables. Consider the examples depicted in figure. Given an entity table S, an attribute table R, and the joined table T, we could map the table S and table R into the matrix S and R. And in the meanwhile, we generate the indicate metric J according to the relationship between table S and table R. Then we can verify that the normalized metric of table T can be constructed with a S and JR. Here, the indicate metric J is defined as JXY. JXY is equal to 1 if the X row of the foreign key in the table S is equal to Y. For example, J11 is equal to 1 because the foreign key of the first row of table S is equal to 1. Using the normalized metric, we could further use linear algebra to accelerate the FSVM. Here, we give the experiment result. We use 9 real data sets. The table summarizes the statistics of the data set. We compare 3 versions of SVM, including baseline SVM, which learning after joining, and FSVM is the primer method proposed in our paper, and the MFSVM, which further uses the normalized metrics and the linear algebra operators to accelerate the SVM learning. The running time on gradient descent optimization method is presented here. And here is the running time on SMO optimization method. We could say that our MFSVM method performs the best, followed by the FSVM and the baseline SVM. This demonstrates the proposed method, including learning over joins and the normalized metric boost the efficiency of SVM. At last, we conclude our work. The key contributions of our work are listed here. First, this is the first attempt to study the problem of learning SVM with Gaussian kernels of normalized data. Second, we proposed a factorized approach that decompresses the Gaussian kernel function computation into joins and implement it into 2 SVM optimization methods. Third, to further boost the efficiency, we leverage metrics to represent normalized data and transform the process of SVM learning into linear algebra operators. Fourth, we conduct extensive experiments with 9 real datasets to demonstrate the efficiency of our proposed method. That's all. Thank you.
Thank you. So, any question? So let me unmute.
Yes, I have questions.
Yeah, go ahead.
First, I want to ask that in your algorithms, I find that I could not quite understand how you utilize the tables to help you speed up this process. This is the first question. And the second question is that
let him answer the first question first, and then
okay, then answer first question.
So any author is here from that paper?
Okay. Can you hear me?
Yes, we can hear you. Can you answer that?
In our paper, we assume the training dataset are stored in the database tables, and the there are multi-tables, and the traditional machine learning area would join those tables and input the dataset to training. And we see the data redundancy in this processing, and we use the join learning over join the structures designed in these papers to accelerate the processing.
And I have a second question. The second question is that do you still need to compute the whole or store the whole kernel matrix in order to help you to do the training help you to do a SVM training?
The whole kernel tables is still should be computed, but the computed processing can be accelerated by our learning over join structure.
Then do you still need to store a very huge table? That's mean
for the kernel function results, we still need to store the bigger table.
Okay.
But not the feature but it's not the temperature bigger feature tables. We don't need to install it. We just store the result table.
Store the result. That means you can bypass that or do not need to store it. And a little bit confused here.
Yeah, I mean the big temperature table in the computation processing is avoided, but the result kernel table is still needed.
You mean the final results?
Yeah.
Of the prediction, the final, the classification 1 or -1 and something, and okay, yeah. Okay, and thanks for answers. Okay, I do not have any other questions.
Thank you.
Thank you.
Any other participant? If you don't have any question, then I would like to conclude the session, and I would like to thank you to all of you to attend this session. So this will end our session, and thank you. So you can stop now. Bye, guys.